Nuclear magnetic resonance, NMR, is a powerful analytical technique that explores the spin states of nuclei in a magnetic field. By understanding these interactions, we can unravel molecular structures and dynamics, leading to advancements in chemistry, medicine, and materials science. Join us on this journey into the fascinating world of NMR. Nuclei, the central part of atoms, have an intrinsic property known as spin, which makes them behave like tiny magnets. This spin generates a magnetic moment, and when placed in an external magnetic field, the spin can align in one of two ways, parallel or anti-parallel to the magnetic field. The parallel alignment represents a lower energy state, while the anti-parallel alignment represents a higher energy state. When a magnetic field is applied, it causes the nuclear spins to split into distinct energy levels, a process called the Zeeman effect. This splitting occurs because of the interaction between the nuclear spins and the external magnetic field. The energy difference between these two states is proportional to the strength of the magnetic field. This interaction forms the fundamental principle behind nuclear magnetic resonance, NMR. The population of spin states is influenced by various factors, starting with thermal energy. At room temperature, most nuclei are found in the lower energy state due to thermal energy, although a smaller fraction resides in the higher energy state. The Boltzmann distribution law governs the population of these spin states, with a slight excess of nuclei in the lower energy state. Temperature has a significant effect on the population of spin states. Higher temperatures excite more nuclei to the higher energy state, while lower temperatures tend to favor the lower energy state. At thermal equilibrium, the number of nuclei in each state stabilizes, and the distribution follows a specific ratio. This ratio depends on the temperature, the energy difference between the states, and the strength of the applied magnetic field. The transition of nuclei between spin states plays a key role in nuclear magnetic resonance, NMR. When electromagnetic radiation of the correct frequency, matching the energy difference between the spin states, is applied, nuclei in the lower energy state absorb energy and transition to the higher energy state. The energy needed for this transition is provided by radiofrequency radiation in NMR experiments. This energy absorption generates an observable signal in NMR, which is crucial for the technique. However, this transition can only be observed when there is a significant population difference between the two spin states. The greater the difference in the number of nuclei in the lower and higher energy states, the clearer the resulting NMR signal. The Boltzmann distribution law, which explains how nuclei distribute between different energy states in a magnetic field. At room temperature and under typical magnetic field strengths, the number of nuclei in the lower and higher energy states is not equal, but the difference is small yet significant. For example, at a magnetic field strength of 23,500 Gauss, there is a very slight excess of nuclei, approximately 0.001%, in the lower energy state compared to the higher energy state. This imbalance is crucial for energy absorption, allowing some nuclei to transition from the lower to the higher energy state when they absorb electromagnetic radiation at the correct frequency. This process is what generates the NMR signal. However, once the system reaches equilibrium, meaning that energy absorption and relaxation processes balance out, the system becomes saturated. When this happens, no further transitions occur, and as a result, the NMR signal disappears. Continuing from our discussion on the Boltzmann distribution law, let's now explore two key concepts that influence NMR spectroscopy: saturation of the system and signal intensity. In NMR, energy absorption occurs when nuclei transition between energy states. However, when the system reaches thermal equilibrium, further absorption of RF radiation ceases, and no additional transitions occur. At this point, the population difference between the lower and higher energy states becomes equal, meaning no net energy absorption can take place. This condition is known as saturation. When the system is saturated, the NMR signal disappears, making it difficult to obtain meaningful spectral data. The strength of an NMR signal is directly related to the population difference between the lower and higher energy states. A larger difference in populations results in a stronger NMR signal, as more nuclei are available to transition between energy states and absorb energy. Several factors influence signal intensity. Magnetic field strength. A higher magnetic field increases the energy gap, enhancing the population difference and boosting signal intensity. Temperature. Lower temperatures help maintain a greater population imbalance, strengthening the signal. Relaxation processes. Efficient relaxation ensures that nuclei return to the lower energy state, allowing continuous signal generation. The intensity of a nuclear magnetic resonance (NMR) signal is primarily influenced by several key factors related to the interaction of nuclear spin states with an external magnetic field. Understanding these factors is crucial for optimizing signal strength and improving the sensitivity of NMR spectroscopy. Population difference between spin states. The intensity of an NMR signal is directly related to the population difference between nuclei in lower energy and higher energy spin states. A greater difference leads to a stronger signal, while a smaller difference results in weaker intensity. Energy difference and its influence. The population distribution between spin states is governed by the energy gap between them. This energy difference determines how many nuclei occupy the lower energy state compared to the higher energy state, affecting overall signal intensity. Role of the magnetic field strength. The energy separation between spin states depends on the strength of the externally applied magnetic field. A stronger magnetic field increases this separation, leading to a larger population difference and, consequently, a more intense NMR signal. Effect of the magnetogeric ratio, gamma. Each nucleus has a unique magnetogeric ratio, gamma, a fundamental property that influences how it interacts with a magnetic field. The greater the magnetogeric ratio, the larger the energy difference between spin states, resulting in enhanced signal intensity. Impact of gamma on signal intensity. The intensity of an NMR signal is significantly affected by the magnetogeric ratio of the nucleus, as the signal intensity is proportional to gamma cube. This means that nuclei with higher gamma values produce stronger signals, making them more favorable for NMR analysis. Today, we explored the powerful technique of nuclear magnetic resonance and its role in studying molecular structures and dynamics. By understanding the interaction between nuclear spins and magnetic fields, we gain valuable insights into chemical and biological systems. As we move forward, applying this knowledge will enhance our research capabilities and drive new innovations. Thank you for your time and engagement. We hope this session has deepened your understanding of NMR and its significance in scientific research. Feel free to reach out with any questions, and we look forward to your continued exploration of this fascinating technique.